Well, it doesn't seem, let's struggle a bit. Let's say, well, okay, MIT professors are always right, and if you believe that, you clearly haven't watched the message forums, which are full of, oh, I didn't say that right, did I? You should always sort of question things. So let's try some thought experiments. Suppose we use a flip-flop to decide. Okay, a flip-flop clearly takes in, a D input and a clock edge, and the idea that the flip-flop should work correctly, and it might be that if the D input changes too close to the clock, I won't quite remember, get the right answer. But Q, in theory, should be either a 0 or 1 on the output after TPD. So this seems like the circuit will work, and in fact, it's tempting to think that it will work. And the thing that the belief that you have about why the circuit works is that you're assuming that the Q output is always going to be reliably a 0 or a 1 after TPD. And what I'm about to show you is a little analysis that suggests that, in fact, that's not true. And we're going to revisit our basic diagrams about how our little positive feedback loop works and discover an awkward situation when, in fact, the Q output isn't not a digital output. If you violate the dynamic discipline, it is possible with a register to get a non-digital output from the register. Okay, so it's not that it's not remembering the right thing, it's actually not remembering a legitimate digital value, at least in the time interval that we're talking about. Okay. So, do you remember this diagram here where what we did is we first of all thought about we made a positive feedback loop, which initially we drew like this, like so, but to make it settable, we basically used a mux to help us figure out like so. So we used a mux to implement something that when G was 0 was in a configuration that provided a positive feedback loop, and when G was 1 allowed us to set the value that we wanted to remember, with the latch at that point was transparent. And so when we looked at when we did the simple analysis of this positive feedback loop, we had two constraints that the loop had to obey. One was the sort of V in to V out characteristic of these pair of inverters, and that's this S-shaped curve you see here, the standard sort of voltage transfer graph of a buffer. And then because we've connected the output to the input, the other constraint that must be satisfied is in fact that V in equal V out. And we've been happily living in the world that either we're in the state that V in and V out are high, or that V in and V out are low, and we sort of said we'd get back to this thing if we balance something right in the middle. And in fact, what we're going to really concern ourselves with today is what happens if somehow in the process of changing clock and D, or G and D, both latches and registers have this metastable state problem, we actually end up balancing the feedback loop right at this metastable state. And we'll talk about what it means to be metastable. Okay. Alrighty, so suppose that we actually somehow have gotten this thing with a voltage sitting here, okay, in which that corresponds to V in equals V out. So this is the V in equals V out point. We were changing the voltage in such a way that at the time that we switched this multiplexer from being open to being closed, the latch to being closed, we went into this memory mode that the voltage at that magic moment turned out to be right at this middle balancing voltage, the V in equals V out voltage. Okay, so that voltage turns out to be between both our logic high and our logic low. So it's not a valid digital output. And it's unstable. In other words, if we think a little bit about, see down here, if we made a little bit of changes, if we added some noise to this circuit, okay, it didn't matter much because this gate restored values, and in fact the circuit would maintain it would be reliably stay in the state even if some of the electrical nodes acquired a little bit of noise. And the same thing for this state. In this state, that's not true. In this state, that if you get that feedback voltage away from that middle voltage even a little bit, the gain in the inverters will quickly turn it back into a digital value. So it's unstable, or we call it metastable, in the sense that you're sort of balancing at this point, but then at some point, random noise in the circuit, or even if it's just a small noise as created by the thermal motion of the electrons, will eventually cause this thing to jiggle away from this metastable point, and then it will get resolved. The point is that we don't know how long that's going to take. And this is where the bounded time comes in. If you give me forever, I can be pretty sure I'm not going to be at the metastable point forever, for an infinite amount of time. But I can't guarantee for a certain bounded amount of time that I'll have come out of this unstable middle state. Okay. And the idea is that the closer we'll get to this balance point, the longer we're likely to be in this metastable state. And I'll give you an analysis for that. The thing that's true, sort of about the universe, that if you have a bistable system, a system that has one of two stable equilibriums, you always end up with a metastable state, because in the process of transitioning from one of the bistable states to the other, you'll always pass through one of these metastable states. Okay, so I'm flipping a coin. Well, it's true that the coin could be balancing on its edge for a little while. Now, that's not stable. Typically, a small mechanical perturbation will cause it to fall over. Okay, or a horse race, the two horses can be sort of arbitrarily close together, and it might be that they're so close together that if you have to decide the finish of the race within 10 seconds, you may not have enough time to make a decision of who was first. Okay, so every bistable system exhibits this, and that's sort of a surprising behavior, and it's that behavior that we're going to spend some time trying to analyze. So what would you actually see if you violated the dynamic discipline on a flip-flop? I mean, what sort of bad behavior, bad flip-flop, what would we expect to find on the output if we're experiencing this metastable problem? And if you hooked up the scope traces, you'd see probably one of two things. This is basically a superposition of many output traces, okay, based on many experiments of making clock and D happen at sort of the same time. And what you discover is that you can see the output sort of sit in this metastable region, and then over some period of time, it will eventually come out of the metastable state and resolve itself either to 0 or to 1. Now, at the point when it comes out, it sort of lost its memory about where it was. I mean, it's not like, oh, I'm going to be a 0 eventually, I'm just going to take a long time to get there. It's once it gets into the metastable state, the resolution is usually random. So the resolution here, once I've been in the metastable state, doesn't depend on some minuscule detail of D and the clock timing. Okay, so. And the idea, you see these many traces, and you can see most of the experiments got resolved very early on, but there's a sort of this exponential tail of experiments that are still in the metastable state after some fixed period of time. Turning that around, if you say, look, I'm going to come look at this fancy trace that you're showing me in the oscilloscope after 1 second, it is still true that there might be, over many trillions and trillions of experiments, that there may still be 1 or 2 that haven't been resolved by that time. So that's what I mean by something that's not 100% reliable. Right, there's still some probability that I'll be in the metastable state after any specific period of time. Okay. The other thing that can happen is the thing starts going into some sort of oscillatory behavior. And whether you see this resolution, actually at the middle voltage and then it gets resolved some amount of time later, or you see oscillations, depends, if you will, on how long the sort of time constant associated with that feedback loop. And I've actually seen both behaviors. You can imagine that in a digital system, a value that's in the middle or a value that's oscillating is sort of bad news, right? I mean, you can't really expect your system to work correctly. And in fact, in the 70s, we worked on such. We were building digital systems here at MIT, and in particular, we were building one of the first bitmap displays. And we discovered that part of the timing of that circuit had some metastable behavior, which would cause, little bits on the display to sort of randomly turn on and off. And it was very tempting to just assume we had made some mistake in the design. But in fact, what happened was that we were actually seeing evidence of metastable behavior, right? Is that the system was behaving incorrectly for this fundamental reason.